from university and Oxford University results from Liverpool Institute. And he will be around until Thursday. Yeah. And today he's going to tell us what other people miss when they look for anomalies in CMB.
Okay, so I'm going to talk about the anomalous odd-parity preference of CMB anisotropy data. That's the main topic for today's talk. So outline was like, so I'm briefly review the basis of CMB anisotropy, and then anomalous odd-parity preference found in the large scale CMB data. And then I'm going to discuss our investigation on the cosmological or non-cosmological origin of this anomaly. And then for a moment, I'm going to get up the main topic slightly and discuss the lack of angular correlation of CMB data, and then show the angular correlation anomaly and odd-parity anomalies are deeply related. And then I'm going to list the various CMB anomaly and group some of them by common feature. And then recently, X-word hyperbolic emission was suggested for the underlying origin of various CMB anomaly, and I'm going to present our investigation on this hyperbolic emission using the frequency spectrum signature. And then I'm going to summarize my investigation and end with the optimistic prospects. So here, this is the famous whose guy's CMB map. And then when you have this CMB map, you usually decompose them into the spherical harmonies. So this spherical harmonic composition is like the analog of a Fourier transformation on a two-dimensional sphere. And so when you have this decomposition, you can compute the angular power spectrum, which is related. So for certain multiple L, you get information on a certain angular scale, which is roughly given by this. And for the whole sky coverage, the angular power spectrum is simply given by this. But for incomplete sky coverage, it's a little more complicated than this. And so these are the W7 power spectrum data. And then there's a first acoustic peak and the second acoustic peak. And the location of these acoustic peaks are sensitive to the geometry of our universe and ingredient of our universe. So by feeding data to the theory, we can impose constraint on our universe, cosmological model. So that's the pretty big difference in the anisotropy. And then now, let's look for something anomalous. So when you have some general
question about the previous slide, the power spectrum you showed, is that just not the standard pipeline? Because normally when you see W map power spectrum, it's the thin power spectrum, right? But this is not thin.
Okay, so this is a more correct representation of the W data. So, okay.
It's not thin, right? It's
B?
L by L.
Huh?
It's not thin, right?
Right. Yeah, because so when you bin data, so the binning, people usually bin them to make them more look better. So this is the correct way. So you never use a bin data to feed cosmological model. And quoting my senior person around me, you can get whatever you want by binning. I'm choosing the bin size.
That's a bit strong.
So here, when you have just as a general function, you can control the symmetric and antisymmetric part under the parity inversion. It's similar to it's just like you construct the symmetric and antisymmetric matrix. It's quite similar to that, and then these are just purely mathematical. But because of the functional parity of spherical harmonies, you may easily show the symmetric part contains only even multiple, and the antisymmetric part contains only odd multiple. So here I made the simulated CMB map. The left one contains only even multiple, right one contains only odd multiple. So you can see, so these are the opposite direction, exactly same pattern, and here same pattern but different sign. So nothing anomalous with this because it's a purely Gaussian CMB, purely Gaussian simulation. So now let us look at the power spectrum of W7 data. Here, these are the data and theory. And you may already notice that there's some oscillating pattern up and down, and then for some surprisingly, there's always like excess of power in an odd multiple, and then power deficit and an even multiple. And so here we sum the powers, angular power spectrum to certain multiple range, P plus, P minus. P plus contain only the even multiple and odd multiple. You compute the ratio between these two quantities. It's below 0. And I plotted the ratio for various LMAX, the upper bound of this summation. And this is the theory, and you can see the dominant data has all the lower value than the theory. And we found when the LMAX is the 22, statistical significance is the highest. So here the p-value means the fraction of simulation which has a lower value than dominant data. And then later another group used the Planck pipeline to apply the Planck pipeline to the dominant data and then estimate the power spectrum themselves and then confirm the result. We simply use the maximum likelihood method in simulation, but they use another method, which is the extension of the Peckmark method. So
is that based on the ILC?
Oh, no.
Is that based on?
The foreground we use V-band and W-band. Oh, okay. So what do you mean by IC band?
So the galaxy mass.
Okay, here this power spectrum are so here we estimate the power spectrum only for the simulation, and this power spectrum estimation was done by W-band team. From foreground we use V-band and W-band with the foreground mass.
Okay, so the galaxy was being masked.
Right. So it's derived by W-band team, this curve.
So should we believe
So foregrounds are heavy.
sorry, what?
Foregrounds are masked out.
Right, yeah, but the galaxy masked out large angles, right? And so should we then trust the points below?
Right.
Something,
Right, but that's why we use the simulation. For simulation, we use the same mask. W-band team use.
So that is becomes all of the function. You correct for a movement of data plus increases on the data. And that is what you do.
but your ability to measure the low-level multipole must be compromised, though, right? Since you're masking out large portions of the sky.
Right, yeah. So if your mass is too large, then you cannot. You have to do the data. But this is with that. And you have all the multiples.
The simulations are also counted for that.
Right.
And so if you put error bars on your right,
It gets larger. I mean, the error bar gets larger because of the masking.
no, your blue line on your right.
Yeah.
Yeah, error bars.
Right.
How large are the error bars?
Let's see.
How much do they believe the deviation of the observation from here?
We don't have the error bar here, but we just simply fix the LMAX and then compare the p-value.
The random error bar is reflecting the scatter and the red points.
Because it's not random, because when you increase the LMAX, there's an increase of so if you increase the LMAX by 1, you added an even or odd multiple. That's why it's fluctuating.
Well, I was saying that's something, there's no systematic, nothing that's systematic error bar. The spread
Yeah.
is due to just the changing the amount of the part.
Right. It's because you're changing LMAX. So it's a purely theoretical view. Okay. Yeah.
And so does your 99.8% preference, does that include the fact that you got to choose what LMAX was? I mean, that choice is,
Oh,
you just
right.
chose LMAX to be like,
Yeah, it's a posterior bias and cherry picking according to the one of the referee of one paper. but we followed the referee's recommendation and we kind of the marginalized over the choice of the LMS thing, but we got the same level of statistical significance. I mean, it's some high, I mean, less significance, but the same order. And another thing is it's not really sensitive to the LMS because you get a suppression, lower value for various range of LMS. So it's not really cherry picking. Because when you have upper one and the lower one, depending on LMS, you can say that, but there's a general tendency over here. So that's a posterior bias in the thing is not that big. So now, okay, so.
Just before you move on,
sure.
Go back there. So the theory curve,
Yeah.
The fact that it's not centered at one at large scales, it's supposed to be a little bit greater than one. Is that just coming from the ISM, the fact that the even the quadrupole is supposed to be bigger, or
No. Because we exclude the dipole.
okay.
If you include the dipole, which I think is pretty close to one. Dipole is almost like as big as quadrupole, and by subtracting the big part, you already.
It takes a while for the Anomalous to compensate.
And okay, let's, so instrument noise is the first one to play. So there's a two channel for each band. So we subtract the one channel from the other and then construct the noise map. And then we plotted this P plus P minus here in whether agrees the white noise, which the ratio of the white noise, and Y7 data here. This line is showing the slope, which corresponds to the ratio of W7 data. So the slope is much lower W7 data. So noise, since it's unlikely that it looks like noise is not the first one to play. And so another one is a residual full one. So we subtracted the full one with the W band from 3 band because the 3 and W band are the data maps or part spectrums are estimated. So yeah, we are trying to mimic the what W team did as much as possible and added the simulated CMB and plotted it here. Still, it's very unlikely that such ratio presents a residual full-one. But still, residual full-one is not completely ruled out because you may see from here that the frequency spectrum of the full-one component varies very slowly between V band and W band. This difference is quite small. So then, even if let's say the full run in V band is quite big, but almost same as W band, but they cancel out, so you don't see big effect here. But still, it can be quite large. I mean, difference may be small. So this rules out diffuse full run such as synchrotron or such rapidly varying frequency spectrum full run. But some astrophysical contamination of slowly varying frequency spectrum may not pick up by this test. But here we did not find that anomaly and Pascal effect because we estimate the p-value using the Pascal simulation. So Pascal effect is in the simulation. And we also checked this symmetry using the Pascal CMB map. IRC map, we got full run mass, we got the same symmetry at the same level. So we did not find the definite cause. Okay, so if it's not cosmological, what can the cosmological origin can be? So first we can think of transplantation effect. The transplantation effect is the oscillatory feature on a primordial power spectrum. As this term shows, there's oscillation in the primordial power spectrum. So for certain values of this parameter, it may produce such a symmetry. But I tried to fit this to the government data, but it seems like when it fits well for low L, it does not fit the high L. So given this amount, so maybe we may need a more sophisticated model than this probably. And another possibility is
Are you changing the transfer factor or something?
Changing what?
So are you changing the initial vacuum state?
I don't know really technical detail, but these are well, they are from my limited knowledge, they use some oscillation. And there are many models. And then these are the formula by the WMT to represent the class of such models. So this is not only one model. The second model considered by the WMT is there's a logarithmic dependency here. And another one is you may say primordial fluctuation. So here, decomposition constants ALM is related by imaginary part of primordial fluctuation, or when it's odd multiple, and real part when it's even multiple. So here, this is a primordial fluctuation in a Fourier space, and then you can say the real part may be suppressed compared to the odd part. Then you can say that the base of the primordial fluctuation may be constrained to the certain range of angle for very large angle, for very large scale. Here, this corresponds to the 4 gigaparsec current universe. And these are the two possibilities. And so these anomalies are related to the CMB power spectrum, and the CMB power spectrum are the cosmological parameter and model fitting are mainly based on. So we try to fit the cosmological model using only even multiple and odd multiple. So here the black curve are the cosmological model favored by the whole data set, and then by odd multiple data set and even multiple data set. And you can see there's a parametric tension. And then and then this overall tension is more than 2 sigma. And we also noticed the tension in the spectral index is high. So we also consider the running spectral index and found the tension is getting even higher when we added the. So it's like they are trying to run it from each other. So
where is these two sigmas? Sorry.
Oh, it's not from here, but we did a likelihood ratio test, and the overall likelihood is by more than 2 sigma. So so it's the total tension.
Well, what does that mean?
So this is a tension for a single parameter. So overall tension.
Oh,
So
okay.
there are many parameters.
So if you sum up all these, like,
Yeah, right. No, it's kind of standard way of there's a standard way of doing that. Okay, so now for a moment I'm gonna talk about the CMB angular correlation. So when CMB angular correlation, you correlate the one pixel and the other pixel now are different direction.
Is that equivalent to just checking if they're summing up all the tensions and all the parameters? Is that equivalent to just say to test
Okay,
the
so
same?
when there's a
Same
no
as your initial test?
when there's no degeneracy between cosmological parameters, let's say there's no covariance between different parameters, you can simply multiply all of them.
Right.
But there is a covariance. So spectral index is degenerate with like baryonic density.
Right.
So you cannot simply multiply all of them.
Right. I'm just saying, isn't that sort of equivalent? If you do that for all the parameters in your model, isn't that equivalent to just your initial test that you show them in the second slide, where you see how steady total
Right.
tension at 23 volts?
Right. Yeah.
So just also on that constraint there, you including polarization data. I would guess that emo polarization doesn't have much.
We didn't make a splitting for polarization data. We used all polarization data.
Use all polarization data.
We did the splitting only for the temperature data.
Do you see any of this even odd power parity in emo power spectrum?
No.
It's a large angular scale. It's
No, we did. I mean,
dominated.
we found a slight tendency, but the signal to noise ratio is really low. I mean, it's quite low. So you don't have such a high statistical significance because it's kind of swamped by noise.
Right, okay.
And how many multiples did you use for
We use only the government data only, so it's like up to 1,200 or 1,100. And here, so these are the angular correlation. So So these blue ones is from the simulation. We use the simulation, actual simulation, and the correlation from simulation, so that we can take into account the Tosca effect. So we generate a lot of Gaussian lambda CDM map, and then mask it, and the computed angular correlation. This spread is correspond to the one sigma interval, and these are the data. IRC to Skynet, full run is the prevent, or we ran with the K275 full runners, which retains about 70% of sky, and they agree quite well with each other. And so you may see here, there's a lack of angular correlation, it's quite close to zero. And also, this is known since COVID data, and here we also know the lack of angular correlation at small angle. So because we are scientists, we should do more rigorous than that. Here, these aesthetics are defined by the dominant.
Sorry for interrupting you. This is the angular correlation of, this is just the normal angular correlation. There's no parity.
Right. I'm slightly off the main topic.
Okay.
And I'll get back. I'll show you the practices related. So these aesthetics are defined by dominant Kim, and then they found this angular scale, this range of the angle. This value is so small, and only this small fraction of simulation has such a low value. And we also investigate the small angle correlation using this similar statistic, and we got this p-value. It's not as low as the large angle case, but it's quite low. So in terms of the angular correlation, we are kind of bad shape because only this small window angle makes the agreement with the data. So now there's the instrumental noise. We checked this by repeating the similar investigation I mentioned before for parasiting. We found the noise map has a very small noise, and aesthetics of noise map is smaller than data by order of 3. Residual form smaller by order of 4. And cost sky effect is included in the simulation, and also angular correlation in the full sky medical programmers at the same level. So we also checked the dominant Kim simulated data, which include the realistic noise model, residual foreground, or the non-radiometric effect. But the aesthetics of the dominant simulation is higher than data by a factor of 20 for large angle and by 4 for small angle. So it's not non-systematic effect. So instead of that, we try to
So the aesthetics here that you're talking about, this is a small angular scale, right?
Both. 20, large, yeah. So here, in terms of the ensemble average, angular correlation is equivalent to the angular power spectrum. So PL is a Lagrange polynomial. So when we think of the ensemble average, angular correlation is a simply linear combination of the angular power spectrum. So they're equivalent. So then it makes us think about, okay, so the anomaly power spectrum may be related to the anomaly angular correlation anomaly. So for low L, there is a sum plateau. So this is almost constant. So here, alpha and bison are some positive constant. And we added the even and odd parity asymmetry by this term. So for even multiple, there's a suppression. For odd multiple, there is excess power excess. And then you plug this in here, and then you get this. And then the second term corresponds to normal angular correlation expectation value. And then this arises in presence of the odd-parity preference. And so I plotted this function here, and you multiply some positive constant this plot. And if you add this, somehow you end up it leads to the suppression of the angular correlation in a large angle. So we may say, okay, so odd-parity asymmetry and low multiple is in fact anomalous origin of the lack of large angular correlation. But still, the fundamental explanation for this is still unclear.
So what are FNG? And I can understand.
Yeah, sorry. Because this is more like some you plug in here, and then it's more like the summation of the terms of polynomial up to certain elements. You plug this here and split at this L, and so this is more of the summation of the terms of polynomial. You take this out of summation, and then this is more of the FNG. So what FNG is more like the Lagrange summation of weighted Lagrange polynomial of even multiple or even the odd multiple, even or odd multiple. So yeah, simply I rearrange it into this terms. So mostly it's the Lagrange polynomial.
But what did you expect? I mean, this is exactly the large scales that the ISW effect should be making a deviance from the Sacco plateau. So, I mean, if you put that in, does this cancellation still occur? Because you've assumed that it's that CO is it's flat for L. So you're basically assuming no integrated Sachs work. Then would you get the same cancellation if you kept this integrated?
Yeah, it's more of a qualitative proof. So one of the reasons I mentioned Sacco plateau is we need to instead of we need this factor L plus 1 to kind of get close to a constant value. That's why I mentioned Sacco plateau. But this is not really exact, but it's more qualitative. Also, this pi scalar, I don't think it's a constant. It should be some dependence on L. So, but but at this moment, that's the best we can do. So now these are the CMB anomalies. And I'm not going to the details, but there's a various CMB anomalies. But these two multiple vector alignment between quadruple and octuple have a common feature is alignment. And then here, these are the important ones. Low quadruple power, large scale odd-parity preference, that of large angle correlation, as I mentioned before. There can be thought of single anomaly because it can be for instance, like low quadruple. Quadruple is the even multiple, so it may be considered as a part of this odd-parity preference. So you can group this the anomaly, and then these force are all related to power, and then all of these are related to the low multiple large angular scale. And why low multiple large angular scale anomalies are important? Because it's more related to the very early universe. Or we can test the statistical isotropy or inhomogeneity. We can extend our assumption to the larger scale. So these are very important, but there are a lot of systematic because of foreground masking. And also co-spot and hemispherical power spec asymmetry. There's some paper which claim when you reduce make the co-spot approach to zero, the paper claims that 60% of hemispherical power symmetry is gone. So it seems like most of the CMB anomalies are somehow related. So it kind of hint that there might be common underlying origin for all these anomalies because they share many features. So recently this group proposed actual type of that object. Maybe the underlying origin of these various anomalies. This group considered a simple model of the simple morphology, like cylindrically symmetrical around the equator, and then they removed this template from the CMB map, and then they claim the level of angular correlation, alignment, and odd-parity preference are gone. So what is the actual type of the object? That's the remnant of the solar system formation. I just happen to notice tomorrow's colloquium here is about the actual type of the object. It's the remnant of the solar system formation, and it exists outer part of our solar system at distance 48 U, and temperature will be about 44 Kelvin if they are thermal equilibrium with the sunlight solar radiation. So it affects the sky intensity this way. So it is a black body 44 Kelvin black body radiation and blocks the CMB. and this is a causal codec. And if you normalize this spectrum to the CMB anisotropy spectrum, you get this. I plotted this ratio over the dominant frequency. And so, as I mentioned before, this ratio is very slowly changing. So let's say 3 band and 90 gigahertz of W band. So difference is like less than 10%. So it might not picked up by our vegetable one investigation. So how do we, so
What
we
kind of
need,
optical depth do you need to produce the signal?
huh?
What kind of optical depth would you need to produce the signal?
They use this term, but it's more of the, like, let's see. Oh, it's just like counting number of the object of certain mass.
Well, of course, you're actually looking for a signal, not an occultational, which because there's a lot more.
Right.
So the dust is also sitting where it's like,
Okay.
it should be emitting, but I would have thought that that.
Yeah, there was,
Well, this could be.
I think this was the paper that we discussed last year. And if I remember correctly, they were constraining this from the two blocks that they said were signatures of this drive. But I didn't find it convincing that they had implications. They didn't do a cross relation or anything like that.
Right.
It was very well.
I mean, you would expect a signal, right, at that temperature from this enough for that is probably what it was.
Yeah, but
Yes,
that,
that's just one.
Well, look, the external flow is higher. Yes.
Speaking of area, so they just come on 6
yeah, it's true that there is a type of object emission, but the issue here is it important at the frequency? So we need to pick up that emission, but the problem is besides CMB, we have emission from synchrotron, peripheral emission, and dust. So we need to separate all of them. And for polarization, we expect only polarization only in the synchrotron and dust. So these are the parameters we need to determine. So it's 14 parameters.
Yeah.
And
We also get some polarization conceivably on this. It's not possible to get it done.
okay.
Normally they do.
So we can determine those parameters by maximizing the likelihood. Here the X is the difference between the data and the sky model for temperature, polarization, and C is the covariance matrix. And when you maximize the likelihood, at that point you can estimate the estimation error by Fisher matrix. So it seems everything is straightforward and simple, but the problem is there is a non-linear parameter such as spectral index. It makes things very complicated. So you cannot determine those parameters by simple linear inversion. So for non-linear problem, there is a widely used Markov-Chain Monte Carlo method. But because of the huge computational cost, it can be done only for the very low resolution there. But given the expected angular size of the Kuiper belt object, we need a more higher resolution there. So this is not good. So we decided to take a hybrid approach. There is a Levenberg-Marquardt algorithm. It is widely used method for nonlinear minimization and widely used in computer science, and it outperforms other methods for various problems. So as far as the initial search point is reasonable, it provides a very good result. So we tested with the simulation. So we simulate the data we first use the dominant low resolution MCMC result, and we added a 10% and 30% fluctuation for amplitude and spectral index. And then we applied our component separation method, and we got the accuracy better than 10 to minus 4, which is pretty good. So these are the results. So actually, you are the first one to see this picture. My boss is currently out of town here to see this beautiful picture. So you are the first one to see this beautiful picture in the world. And you may see similar picture from the dominant Jaiseung, but they are made by maximum entropy method, not by frequency spectrum fitting. So for some sense, this is more accurate than man-Foreman method. So this
the
is
spectral index like fits across the sky as a spatially variable?
no, for the 5 frequency. So for each pixel, there is a frequency spectrum of the different frequency spectrum, different dependence, and then you fit to the different 5 channel.
Okay, so each pixel has its own like
5 channel. Synchrotron, free, and then it's a K-band and W-band because we normalize the K-band and W-band.
So the spectrum index changes in frequency, but does it change spatially?
Right. Yeah, because we fit for each pixel. So each pixel doesn't know about all the
Does it
pixel.
change randomly or does it change just look at the result?
Actually,
I don't know how to see the spectrum.
not here, but when you draw the histogram, most of them are synchrotron emission is mostly like -3, and pulse is mostly +2. So it agrees with the standard model. And these are the polarized synchrotron and bus. And now finally, you cannot it's pain. But these are the right. So I retained the only pixel of the pixel which are apart from the 0 value more than 2 sigma and 3 sigma. There is a huge cluster of pixels here, there, and so I convert them to the thermal temperature. So it seems like there is some emission from Kuiper-Belt object in WMF data. So, but still we need to cross-check and do more investigation. But our preliminary results show there is a non-negligible emission from Kuiper-Belt object in a WMF frequency. So, but
these coordinates.
it's a ecliptic coordinate.
So you cut this as
This? Yeah. Because here is dominated by the diffuse Foreman, so error bar is really large, so it's kind of excluded because of large error bar. So error bar, because of dominance of diffuse component like a synchrotron, uncertainty propagate to the Kuiper-Belt object and shadow it. So we don't have good accuracy there because of uncertainty of diffuse Foreman. Because this error bar is made by Fisher matrix, it's a marginalized error expectation. So errors on the diffuse synchrotron and all those diffuse components, they are marginalized. So that's we have a large error bar. So we have some sigma there, but I'm showing only the 2 sigma and 2, 3 sigma. So it's not like it's not there, it's there, but we have less confidence there. And
So lots of your points you're saying show up at the folds, ecliptic folds.
yeah. Oh, because
That's the claim?
because of the
So why is
Kuiper-Belt.
this evidence for Kuiper-Belt? Sorry, I'm still right here. But
Okay, because ecliptic coordinate, because the Kuiper-Belt object is the expected to the concentrate on here, like ring, like
Yeah,
ring.
right.
This.
yeah, right.
Yeah, but we did
Most of
this.
your points are plotted at the pole, it looks like.
Huh?
Most of your plotted points appear at the pole. Is that
Yeah.
right?
Four?
Like the south pole or whatever. Right?
Yeah.
So you're saying you would have thought you'd see things in the ecliptic if you're not seeing them.
Right. Yeah, so, but some papers said, but there's a 2 kinds of Kuiper-Belt object aligned with this, and then scattered within the 40 degrees from the equator. So this does
So
not.
why are you calling this Kuiper-Belt?
Huh? Why? Because this is one of the astrophysical emission, which kind of similar to the CMB frequency spectrum. When it's similar, it cannot easily picked up by those residual Foreman patterns, or they kind of disguise themselves as more like a CMB.
But why does the ecliptic plane have bigger noise? So I think it's,
Oh, here? Oh. So, yeah.
so that's not ecliptic.
Right. So you just remember this line, and this line goes like this. So this line goes like this.
Yeah.
those like very strong synchrotron emission,
So you could
it
just
shape like this.
Yeah, it's kind of, you couldn't have seen it in the center of that plot.
You can see the anti-galaxy will come by hand, and you can see the anti-galactic.
Yeah, so
Yeah, if you
so
rotate
he's,
it.
he's saying at the galactic pole, you can see the eclipse. Things are off the eclipse, but conceivably associated.
She's kind of running it on the far left of the plot, so it actually picks up again like that galaxy.
Right.
If you rotate the 180 degrees around, it would be more obvious.
Yeah.
Far left.
So
Yeah.
if you plot it here, it goes more like here and there. This is more like here, here. And so now we did some sanity check, whether we did some mistake in our to make sure I didn't do any mistake in our coding. I reconstruct the microwave sky for various frequencies within the government of K-band and W-band, and then it's more like using the component separation result, and then it seems like it makes sense. So now it's increasing, and then it's gonna bounce back to the low frequency once we reach. Now it's decreasing. So now it's going back to the K-band. And it seems like our component separation method didn't have much of the data flow because it's kind of consistent. Okay. So now, conclusion. There is an anomalous excess in even odd multiple and deficit in the even multiple and the low multiple data. And this anomaly in the power spectrum requires special attention because it may lead to the bias on the cosmological feeding and parameter. It may lead to wrong conclusion. So there's a lack of correlation, and in particular large angle. But we find the odd-parity preference is deeply related to the lack of large angle correlation. And there are many common features in the various in the anomaly, and so it gives a hint that there might be a common underlying origin of all these anomalies. And the emission from the hypothetical second dominant data may not be negligible given our preliminary result. And the Planck surveyor that has a high frequency channel, which is 900 gigahertz. And then as I showed before, those ratio. The frequency of a hypothetical object has a peak at 3 terahertz. So 900 hertz Planck data is going to provide a very good information on the actual hypothetical object, probably beating the synchrotron emission in that channel. So that's quite something. So we are going to have a better result when the Planck data is available. So for today, I'm going to stop here. So thank you.
Again, so you made this fit.
Yeah.
And so what did you, so one of the parameters you had was the optical depth. So what did you measure it to?
Let's see. So the plot I showed, is okay. This one is the one, the tau multiplied by like about 40. The 40 is the ratio of the frequency spectrum. So I multiplied about 40 to tau. So this is basically tau value.
Do you have a map of tau bound?
Actually, I'm not really sure. It's the optical depth, but that's what the term they use for their hypothetical investigation paper. But that's more of the.
But the assumption is that microvolts are like 40 kelvin or something.
Yeah.
So if I take a 30 microkelvin, right. So take a 30 microkelvin divided by 40,
Yeah.
and that's tau, right?
Yeah. So it's more like
10 minus 6,
so it's more of the function of the radius of those dots.
Well, I mean,
10 minus 6
is the right answer.
Okay.
It doesn't measure several.
Yeah, 10, sure. It's 10 to the minus
-6 or 10 -7. You're not seeing the critical arc, you're just seeing dust from the critical arc. If that's what you're seeing at all.
Okay.
But it doesn't seem like it's always
So what fraction of the pixels do you
I know not
get
for this,
2
but-
sigmas on, right? Because then you should get 2% no matter what.
I haven't counted yet, but looks like it's not that clear, but it looks like more than 20%, 30%. But the more important, urgent issue is are they really responsible for those anomalies? That's the more urgent issue for us. So we somehow we can.
But you're saying it's more than the 5% you get. Like even in the noise areas, you should just get 5%.
Okay. Yeah. And another issue is even if the fraction of those pixels, like let's say 50%, 80%, when the value of those pixels are very low, it doesn't matter. So actually the value of those pixels are very more important. Because a very bright pixel cannot have full power spectrum. Like let's say there's a
So in the noise part, right?
Yeah,
in the
yeah.
noisy area,
Yeah, yeah.
where you'll have 5% of your pixels will be 2 sigma just the way it's this Gaussian pattern, right? Just the way things scatter.
Yeah, yeah, yeah.
5% of the pixels will be 2 sigma, and your error bar is much bigger in that area,
Yeah, yeah,
right?
yeah.
And so those pixels that do scatter to above 5% will be much brighter, right?
Yeah, yeah.
And do you see consistencies like that? Do you have? I just put in Gaussian numbers as tau and use your noise map. Do you get like how? Do you get the same end? Do you see an excess of beyond that? And you look for those things.
Okay, so you have the noise, and then could you?
I'm just asking. Have you checked the?
What percentage of pixels are more than 2 sigma detections?
I haven't counted yet, but it's more like looks like a 10 or 20%. Yeah, but right. Yeah, but what really matters is the absolute value of this pixel. So, okay, let's say even if it's let's say all of them are more than 2 sigma, but let's say their value is 0.194 Kelvin. It's not important. It cannot affect the CMB and anisotropy that much because it's too small.
If you just feed through like a full simulation of all points in the Anomalous and a reasonable galactic foreground,
Yeah.
and you're just selecting out what look like a hot isolated pixel, then what does it look like? Does it look comparable, or if you just do there are full simulations out
What do
there.
you mean by full simulation?
Well, if you have a simulation which includes everything but includes no actual hyperbola objects,
Okay.
then you get stuff out that looks like hyperbola objects.
No, that's not the problem.
That's
You just
not
can't, that's the problem with.
People are pointing at it, but I don't see it.
Does it look better on the screen?
Yeah. Okay.
No.
Yeah. This voltage over here.
Yeah, it's way more.
Yeah.
So this is the plane of the solar system, and this is the galaxy.
Yeah.
Right.
So, 30 microkelvin is
Yeah.
the large number.
Right. That's the 31 club. Many of the pixels have such value.
Right, and if you look at the power spectrum of the guy, even if it is a small,
Right.
if they are totally uncorrelated and it's a large one-K,
Right.
then you should see it in the power spectrum.
Right. So that's why they mentioned
We don't see.
Right. The problem is so its frequency spectrum is quite similar to the CMB power spectrum. So maybe disguise themselves as like CMB, and that's why those groups claim they are the origin of all those CMB anomalies.
No, the power spectrum.
Yeah. So then.
It has a different shape than.
Right. Let's say low quadruple. So in such case, primordial CMB power spectrum should be even lower than current market. So then we need, even if this explanation is correct, then we still need to modify some cosmology animation to quadruple power, and you already have a low quadruple power. And primordial quadruple power should be even lower than the current.
Sorry, I mean that there's a sanity check.
Yeah, yeah.
Now you have this other component. Right?
Yeah.
This is another component that you can create. So you have your CMB power spectrum.
Yeah, yeah, yeah.
Let's say W not power spectrum.
Yeah, yeah,
right?
yeah.
And we fit it to the lumbar CDM plus point sources plus SC.
Right.
Now there is this one more component that you should fit when you run MCMC change.
Right.
And I think if you get the power spectrum of this and throw it in your MCMC change, you will see something.
Yeah, but can you just apply power spectrum to the non-Gaussian system? It can be correlated. I mean, if it's not Gaussian, I think it's better to subtract calculate instead of marginal.
If it is in your data and you take the power spectrum of the W0 data, it's in there already.
Okay. Oh. Yeah. But I'm a little concerned about this galactic equator thing. I don't know if the error is large.
So this is done assuming the dust is 40 Kelvin.
Yeah.
Can I ask about how that changes, like qualitatively, when you change the temperature of the dust? Like say the dust was actually, I don't know, 80 Kelvin.
Yeah, so that would be the next step because we can consider the little variation over a sky. So let's say 44 Kelvin.
I mean, micron size dust range, which is what this will be much hotter than sort of thin molecular ranges.
Yeah, but
it's too small to emit.
Yeah, but given that distance, 44 Kelvin is our equivalent temperature.
No, his point is that they're not perfect red bars.
Oh, right.
They're
right.
terrible red bars. Right? So they'll actually be, I don't know, 80 Kelvin-ish if they're at 48.
Because right. Yeah, so we are kind of assuming some grains of some size.
So I mean, I can tell you the answer. The grains are microns.
Yeah.
Right? So they will be a lot hotter than thermoelectric with the sun.
Yeah, so we are
So
assuming.
it depends on your grade model, but
Yeah.
70 or 100 or something.
Because
So like, I mean, imagine that the dust grains were actually twice as hot. You know how that would change your answers at all?
you mean I changed the temperature and
Yeah, just change the temperature of the dust and say it's 80 Kelvin. instead of 40.
Okay. Let's see. Yeah, then it's gonna.
It's not clear stress like that. They are hotter, but they're also not as good as emitted.
Yeah, that's true.
Yeah, because it's gonna affect this ratio. Probably then.
Well, there, you assume that,
That's a
you
perfect
assume it's
red bar.
black body.
Right.
So I previously penciled.
Okay, so it's not an easy answer.
You can use a more.
Yeah, much more complicated.
It's well known. It's recent. It's well known how to calculate it. There's just a different frequency response.
Yeah, but to get the spectrum, which kind of mimic the CMB frequency spectrum, it should be something black body.
That's probably not way off from the black body.
Well, no, it's 40 Kelvin. That's one of the CMB is 4 Kelvin. So that's what you can say.
Oh, but as you can see here, it's not changing very rapidly. For like synchrotron emission, they change to the different order. But here it's the same order over this range of frequency. Compared to the diffuse, you may see from here, synchrotron. So it's a 30, and then 90. So maybe here it's like a -3. So it's a different order of like 2 or something. But the type of object is the same order. So relatively similar to CMB. Probably if you have a very accurate data, we can do that. But such a small, so that's why they're harder to catch compared to those diffuse components.
But the most disturbing thing is it's not.
Right. Yeah, but if it's a non-black body, I think it will be quite different. It's more easily detected earlier, or easier to detect.
Well,
we have to find the reason
it
why.
should be
less emissive at long wavelengths than black light, and more emissive at short.
I mean, okay, so in that case, is it continuous or it's just?
It's gonna be slowly varying. That's really all it is, right? It doesn't need to be black on. It's always power law.
But still
There's probably,
smooth? Is it smooth?
It's
yeah, it's pretty smooth. Should be.
Hank has observations near the and that goes all the way to 7 to 10 pounds. So I think if you have a template, you can really
Because actually, before beginning this investigation, I started this investigation to invalidate the claim, those groups. But for something, I'm still a little intrigued by the result. Because I was expecting no significant signal from there. But
all right, so let's thank Jaiseung and continue